or if I missed something in the chat. I want to talk about a project or two projects that I've been working on around the tropicalization of principal minors. So these are based on sort of two papers that will hopefully be posted on the archive this summer. One is with Abeer Al Ahmadieh, Felipe Rincón, and Josephine Yu. I think Josephine's here. She can answer questions. And then the other is with Nathan Cheung, Tracy Chin, and Gaku Liu. Okay. So to start out, I'm going to talk a little bit about tropicalization, although I think it, may be familiar to a good number of people here, and talk about sort of two viewpoints on tropicalization. One is really thinking about what's called algebraic or semi-algebraic subsets of R to the M or C to the M. So these are sets defined by polynomial equations or inequalities if we're working over the real numbers. And tropicalization we can think of as a way of understanding sort of in what directions these sets go to zero or approach infinity coordinate-wise. So one way to do this is to take the image of this set under coordinate-wise absolute value. This makes sense either in sets in R to the M or C to the M. We'll get a subset of the non-negative orthant. And then one way to think of the tropicalization is we first take the coordinate-wise logarithm of this set and then zoom out and take the limit as we zoom out for this set. So for example, here in R2, we have a line defined by a single polynomial equation. We could take its image under coordinate-wise absolute value. So then in particular, this sort of branch is going to get flipped over here. And this branch is going to get flipped over here. So we'll get a subset of the non-negative orthant. If we take the coordinate-wise log, so in particular, we are going to delete these we ignore points with coordinates equal to 0. And we take the coordinate-wise log. And then what we see is, for example, this branch, all of the coordinates are less than or equal to 1. And as we approach this point with a coordinate equal to 0, then that coordinate is going to go off to minus infinity. And so this branch becomes this sort of infinite branch here, which continues longer than my picture will go. And similarly here, both coordinates are going off to infinity if we go in this direction in a linear way. And so we're going to get a branch going off to infinity this way. And if we were to take this picture and zoom out and take sort of the limit of the zoomed out picture pointwise, then what we get is we're going to find a polyhedral fan with 3 rays, namely the ray 1, 1, the ray 0, -1, and the ray -1, 0. And so the theorem is that the tropicalization is always a rational polyhedral fan whose dimension is at most the dimension of the original set. And in particular, if we work over the complex numbers, then the dimension is going to be equal to the dimension of S as an algebraic set. Okay. Another way of thinking about tropicalization, which is one that might be a little bit more familiar, is really using a field with a valuation on it and then looking at the coordinate-wise valuation under this field. So for example, one way to think about this is if we were to start again with the real or the complex numbers, we could take the Poisson series, what's called the Poisson series over this field, which are like power series, except that we allow fractional powers with a uniform denominator, and we're allowed to have the lowest term be sort of any integer, including negative ones. This is, in particular, a field with a valuation where the valuation picks off the exponent of the lowest term with non-zero coefficient. So in particular, one can think of this as like the order of growth. If you think of t as sort of infinitesimally small, this gives you the order of growth around t equals 0. And there's lots of other lovely fields with valuations that you could use instead of this, but this is the one that I'll focus on today. And then if you have some subset of k to the m defined by polynomial equations or inequalities, you could look at that, the subset of over this field, where you just take the set of points satisfying the exact same description, the same equations or inequalities that held on your set just in R to the m or C to the m. And then in this case, the sort of big theorem is that if you think of this logarithmic limit set that I showed on the slide before, so you get a rational polyhedral fan. If you take the rational points of this, you get the same thing as the image of this set considered over Poisson series under valuation, or minus valuation for some technical reasons. So in our example, we had this line in R2, and we had this whole picture of operations. We took the absolute value, we took the log, we got the tropicalization. What this says is that, we can essentially parametrize. So for example, this ray spanned by -1, 0, we can realize as a Poisson series, as a valuation of some Poisson series in our set. For example, x1 equals t and x2 equals 1 minus t. We take the image, can check that this satisfies x1 plus x2 equals 1. And if we take the image under coordinate-wise valuation and a negative, we get -1 for the valuation of t and 0 for the valuation of 1 minus t. And then similarly, you can realize this ray as the coordinate-wise negative valuation of 1 over t and -1 over t plus 1. You can imagine as t goes to 0, what's happening is these are both growing really large and growing at the same rate. Okay. So that's my crash course in tropicalization. Please feel free to interrupt with questions if you like. What I want to do is I want to talk about taking the tropicalization, applying this to sort of some nice semi-algebraic sets that are going to turn out to have some nice combinatorics surrounding them. Okay, so let me tell you about some nice combinatorics that people have already known. This is, I think at this point, fairly classical. But so for example, the Grassmannian is a nice algebraic variety, and one can study its tropicalization. And there's all sorts of nice combinatorics that comes out of studying this. And you can think of this as really understanding if you have, say, a D by N matrix and look at all of its D by D minors. The tropicalization will tell you how these D by D minors can go to 0 or infinity simultaneously. So in particular, so David Speyer and Bernd Sturmfels studied the tropical Grassmannian. One can think of this as the image, if you take a D by N matrix whose entries are in your field with evaluation, you record the n choose D by D minors in a big vector and take its image under valuation. And these give what's called a valuated matroid of rank D on the ground set N. For example, if we were to work over a Poisson series, we could take an element of the 2-4 Grassmannian over this field. This can be given as the row span of a 2 by 4 matrix. I've chosen this one. We can record its 6 2 by 2 minors, which hopefully I have written down correctly here. And then we take the valuation or minus valuation of each of them. All of these have valuation 0 because the constant term is the biggest, except for the last one in which we get a t. And so the valuation is all zeros except for the 3, 4, 4 coordinate gets a -1. And one way of understanding valuated matroids is to look at the subdivision that this induces on the matroid basis polytope. So here, all 2 by 2 minors of this matrix are non-zero. We could look at the polytope in R4, whose vertices are the indicator vectors of these subsets. So by 1, 1, 2, I really mean the vector 1, 1, 0, 0, the indicator vector of the subset 1, 2. These all have coordinate sum 2, so it lies in a 3-dimensional plane. You can check this is that this polytope is really the octahedron that I've drawn. And so that gives a matroid, and then the valuated matroid says, well, if you take the regular subdivision of this polytope induced by these heights, then each piece of the subdivision will also be a matroid polytope. So in this case, we can imagine keeping all of these vertices at height 0, and then pulling this in the 4th dimension, pulling this one down by -1. What's going to happen is this bottom pyramid is going to break off into its own piece. But we can see that both of these pyramids individually are matroid basis polytopes. Okay. There's other previously known. So this is, we start with some variety coming as the minors of some matrix, and we get some nice combinatorial structure from its tropicalization. There's many other instances of this. For example, Felipe Rincón in 2010 showed that if you start with a skew symmetric matrix over a valued field, and you take what's called the Pfaffians of a skew symmetric matrix, these are principal minors of the square root of principal minors of even size. Then the image of the space of skew symmetric matrices under this map gives what's called a valuated even delta matroid, which maybe I won't define for the moment. But so this is another notion of minors giving nice combinatorial structure. Any questions before we head on to harder things?
So just to clarify that that valuation you drew, cut the matroid polytope into 2 levels. Is that right?
Yeah.
Zero
So that's right. So we have sort of one big pyramid on top that's sort of at height 0, and then the other sort of maximal piece of the subdivision is
Cool.
yeah, at the bottom one, because we've lifted this vertex down.
So you're using like closed intervals in the image of the valuation, I guess, right?
Closed intervals. I don't know if I know what you mean by closed intervals.
Yeah, sorry, never mind.
Okay.
Dave Anderson asks a question in the chat. He says, is Rincon's theorem about a tropical orthogonal Grassmannian?
That's right. So yes. So Felipe actually, the title of his paper is really about the Lagrangian Grassmannian. But you can translate, so if I give you a skew symmetric matrix, let's say a skew symmetric matrix A, then the element of the Lagrangian Grassmannian that I would want to consider is the row span of the n by 2n matrix A. And the condition for being in the Lagrangian Grassmannian is exactly like that this matrix is skew symmetric. Yeah. So I'm rephrasing Felipe's
Thanks
a little bit.
I think that should probably be orthogonal, but it doesn't really matter. Thanks.
Yeah, okay. I'll mention the orthogonal Grassmannian
Okay.
also later. Yeah, thanks. But yeah, so to me, I want to tell the story in terms of minors of matrices, but there's also like lots of other phrasings of. Great, yeah, thanks. Okay. Okay, so I want to tell the story in terms of principal minors of matrices. So let me talk briefly, let's for the moment forget about tropicalization and talk about principal minors of matrices. Sometimes called the principal minor map. So if we start with a n by n matrix, then its image under the principal minor map is going to be a vector of length 2 to the n, where for every subset of 1 through n, we pick out that set of rows and the same set of columns, and we take the determinant, take the determinant of the square submatrix with those rows and columns. Where in particular, we take the empty minor is just 1. You can do this for your favorite space of matrices. I want to, in particular, talk about it for real symmetric matrices or Hermitian matrices over the complex numbers. But so you can study, the image of your favorite space of n by n matrices under this map. You can check that, and so what you're going to get is if you work. So these will be, as I've written them, the image will be real, because we start with a real symmetric matrix, or we take a Hermitian matrix and then we take its principal submatrices. Then all of the principal minors are going to be real. And so this image, whatever it is going to be some semi-algebraic subset of r to the 2 to the n. And you can check that if you start with symmetric matrices, then the dimension of the image is really going to be the same as the dimension of the space of symmetric matrices, which is n plus 1 choose 2. If you start with Hermitian matrices, which as a real vector space has dimension n squared, and you take the image under this map, then you lose a little bit of dimensions from some diagonal scaling arguments. And the image has dimension n squared minus n plus 1. So this is pretty high. It's in a 2 to the n dimensional space, so this is pretty high codimension as a thing. In particular, if you start with a positive definite matrix, so this is a matrix all of whose eigenvalues are positive, or equivalently, all of whose principal minors are positive, then, when you record this vector of principal minors, you already land in the positive ortho. And so one of the motivating questions for these works is what is the tropicalization of this image, which we can think of as the question of how can the principal minors of a positive definite matrix simultaneously go to 0 or infinity. So just as a small example, if we start with a 2 by 2 matrix, we take a 2 by 2 matrix, we know its diagonal entries, and we have, let's say, a symmetric matrix. We have a mystery off diagonal entry. Then what we're going to do, is we're going to record the 4 principal minors of this and see what we can get. So in particular, we record the empty set, which the principal minor corresponding to the empty set, which is 1. We record the diagonal entries, spot on, and then we record the determinant, which is a1, a2 minus b squared. And what we get, the image, is defined, in addition to this sort of obvious equality, is defined by this one inequality that a1 times a2 is greater than or equal to the determinant. And why is this true? It's because the determinant is a1 times a2 minus a real number squared.
Can I ask real quick? I think you may have said this, but it went by me. The map that we're looking at, A goes to the tuple of minors.
Yeah.
Is that, am I meant to think of that as sort of the analog of the amoeba map that you were showing us on the first slide? Or the,
So this
or
is going to be the semi-algebraic set that we then tropicalize.
that you then, oh, okay.
Yeah.
Okay.
So like this is the image, and this is completely like there's no tropicalization. When I write this down, there's no tropicalization that has happened. I have, you know,
Yes,
yeah,
okay,
the
got it.
image
Thank
of
you.
this is
Yep.
just
Got it.
something
This is just an
defined like
embedding of,
polynomial equations and inequalities.
okay. And it
Like the
could,
Grassmannian. To me,
yep, okay,
this is analogous to the Grassmannian.
got it.
We've tropicalized nothing.
Thank you.
Yeah.
Sorry, but it's not an embedding, you said, in general for the Hermitian.
It's
Is that
not an
right?
embedding. Yeah, you lose a little bit. So
Almost.
it's not quite the Grassmannian, but yeah. You can, you know, if you get bored, you can try and think about where where what we lost. Where the hint is, you know, what happens if you scale by diagonal matrices from the left and the right. That's where we might lose a few things. Yeah, but absolutely. So the image of these matrices, that's like a semi-algebraic thing, and that's the object that I want to tropicalize. Like, you know, we took the Grassmannian and then we want to study its tropicalization. Yeah. And in this case, so we take this set in R4. If we tropicalize it, then we get something fairly simple. We just get, so if the coordinate a empty set was constrained to be 1, then its valuation is constrained to be 0. And this binomial inequality turns into just to a linear inequality on the tropicalization. Namely that W1 plus W2 is greater than or equal to W12. And I really want to think about this as the set of functions on the vertices of the 0, 1 cube, where we have, you know, 0, 0, 0 corresponding to the empty set, 1, 0 corresponding to the subset 1, 0, 1 corresponding to subset 2, and 1, 1 corresponding to the subset 1, 2. If we think of these entries as heights on those vertices, and we take the regular subdivision induced on the 0, 1 cube induced by these heights, then what does this inequality say? It says that the sort of the average of the heights of these two vertices is greater than or equal to the average height of these two vertices. So if we look at the regular subdivision induced by the upper hull of these heights, then I mean they could be tied, but if it breaks up into pieces, then the pieces have to be these two. In particular, we're not going to get an edge like this in the regular subdivision. Okay. There's a generalization of this phenomenon, which is the following. So bear with me. But so if we pick, rather than picking one matrix, we could pick many matrices. And suppose I take them all to be Hermitian with entries over the complex Poisson series, and what's called positive semi-definite. So all eigenvalues greater than or equal to 0. Then you could put these into a big linear matrix. So each matrix could get its own variable. You sum them all up and take the determinant. You're going to get a polynomial of degree n in m variables. And it has a property called stability that I don't want to actually introduce. The only relevant piece for us is that if you have a polynomial that comes in this form, that it is stable. And so Peter Brendan showed that if you have a polynomial whose coefficients are real Poisson series and that has whatever this property is, then you know something about the valuation of the coefficients. Namely, that if you look at the function that takes an exponent vector to the valuation of its coefficient, that this function is what's called M-concave. So in particular, this means that if you look at all of the alphas that show up with non-zero coefficient, so you raise them to these heights given by the negative valuation of the corresponding coefficients, and you take the upper hull. This induces a regular subdivision on the convex hull of all these exponent vectors. And M-concavity means that every edge of this regular subdivision is, I guess the way I've written it, I want these to be homogeneous. So maybe we get rid of this. Every edge of this subdivision is going to be parallel to EI minus EJ for some IJ and N. So if we look at just M-concave functions on the hypersimplex of subsets of 1 through n of size d, then this gives exactly the space of valuated matrices, also known as the Dressy. Okay. The way I want to use this is to say that actually, so this is just a repeat of what we saw before. This immediately tells us something about the image of the principal minor map. So if we import this theorem, if we start with any square matrix A, we can look at an associated determinantal polynomial. So I'm going to associate this to the following polynomial. I'm going to take my matrix A. I'm going to add a diagonal matrix of my n variables. I'm going to take the determinant of this matrix. And I claim that the coefficients of this polynomial, I claim that this polynomial is going to be called square free. So the only monomials that show up with non-zero coefficient are going to be square free products of the variables. And that if I look at the coefficient of some square free product, that the coefficient is going to be exactly the complementary principal minor. So just as a sanity check, if I look at the empty coefficient, sorry, if I look at the product of all of the variables, then it's just going to be correspond to the empty principal minor of A. It's going to come with coefficient 1. If I look at the constant term, which here corresponds to S being the whole set N, I can imagine just setting all of the variables equal to each other, and I get the determinant of A. And I leave you to check that the other minors work out as well. But so as a very small example, if I took a 2x2 matrix, A, B, C, D, and I add a diagonal matrix of variables, and I take the determinant, then I get 4 terms corresponding to the 4 subsets of the set 1, 2. And I see if I look at the coefficient of x1, then what I get is the principal minor corresponding to the complementary set 2. Okay. And so then what's the point? Up to homogenization, this polynomial has exactly this form. It's a determinantal polynomial where the coefficient of each variable is positive semi-definite. And so what that means is that if we start with a matrix A that is positive semi-definite, all eigenvalues are non-negative. And I look at the function that takes any subset of 1 through n to the negative valuation of its corresponding principal minor, then the function that I get is M concave on the vertices of the 0, 1 cube. And that will follow sort of directly from this sort of broader theorem about determinantal. So just to do some examples, so we take a 2 by 2 matrix, can claim that the following 2 by 2 matrix with diagonal entries 1 and off diagonal entries 1 minus t is positive definite. This is a real symmetric matrix. Can check that the minors, the empty minor and the 1 by 1 minors are all 1. The determinant, some cancellation happens, and we get a determinant of 2t minus t squared. And so if we take the valuations, we get the valuation of 1 is 0, and the valuation of this is 1, because we have a t to the 1, and we take its negative. And so again, we get a function that's 0 on these 3 vertices, and then we imagine pulling down this top vertex to -1. And so this breaks off into 2 pieces. And so we were interested in understanding what, just to go back to the other slide for a moment. So we know that if we take any Hermitian matrix that's positive semi-definite, then this function is M-concave. We were interested in understanding which M-concave functions you get this way. The answer will be some, but not all. So just to bump up the complexity a little bit, now we can take a 3 by 3 real symmetric matrix, whose entries are now again real Poisson series. Can imagine T is sort of infinitesimally small. And one way to get a positive semi-definite matrix is to write it as another matrix times its transpose. And this is one of the equivalent definitions of being positive semi-definite, is that you can be written in this way. So here I can imagine taking a matrix B with entries over the Poisson series, multiplying it by its transpose. There's no typos. I get this beauty of a 3 by 3 matrix. And then I'm interested in so this has 8 principal minors. So I could record this vector of length 8 and then take its valuation. And the question is like, what happens? And so in this, so one nice thing about this formula is this gives you a formula for the principal minors of A in terms of all of the minors of B. In particular, this principal minor is a sum of squares of the principal minors of B. So for example, let's see if we can do it. If I'm interested in this principal minor of A, say the 1, 2 minor, what this says is that I'm going to fix the columns 1, 2 of B, and I'm going to range over all subsets of size 2 of the rows. Here it's not going to be so interesting. I'm going to take the sum of the squares of those determinants. If we take the valuation of this, then because all of these terms are non-negative, it's impossible for anything to cancel. Sort of the lower order, in general, when you try and take the valuation of a sum, you need to worry about sort of the initial terms canceling out. In this case, because everything is positive, no terms can cancel with each other. And so the valuation of this sum is really just the maximum of the valuation of all of these minors of the times the 2. And so then we can use this matrix, which is simpler, to figure out exactly what this vector of length 8 is, or the valuations of the entries of this vector of length 8. In particular, yeah.
Can you run through that example?
Yeah.
One more time?
Sure.
I was a little confused trying to figure it out.
Let's try a harder one. You're gonna regret this. Let's try the 1-3 minor.
Well, even the easy one.
Let's try the one. Let's be bold and take
Okay.
the 1-3 minor. So this is, we're interested in the determinant. This determinant, I mean, we can calculate it out. But
So,
the claim is that we pick, so here we pick out the 1-3 columns, S, and the claim is that this is equal to the square of, we're going to range over all subsets of size 2 of the columns. So we're going to B12, B13 squared plus B13, 1-3 squared plus B23, 1-3 squared. Let's figure out what that is. So
okay, so t plus 1 squared. So t squared. So.
Yeah, so here we get, so the 1-2 is t squared. The
Okay, good.
1-3 is t squared squared.
Oh, good. Okay. Yeah.
And then the 2-3 is 0. And that should, if we believe math, this should exactly equal this 2x2 minor, because we get this product and then this cross term kills off the 1.
Thank you.
Yeah. And the point is, somehow you could imagine if you have many terms, well, even here we have 2 terms, we have a t squared and a t to the 4. If some of these terms had the same valuation, but the coefficient, but there was like a negative, then those terms might cancel out. And then we wouldn't be able to necessarily predict what the valuation of this matrix is. But because all of these terms are squared, all of like the coefficients of these terms are going to be positive. And so then when you add them together, you can't get any cancellation. And so what that means is, if we want the valuation of A13, we can, or the minus valuation, I'm using max as a convention, then what we can do is we can just look at the maximum of the negative valuations of each of these individual terms, and that will give us the right answer. And so in this case, here, the lowest degree term is t squared, nothing coming from this minor, and nothing can cancel out with that. So that term will survive. And so when we take the negative, we're going to get W13 is equal to minus 2, where this 2 is sort of this 2. Yeah, great, thanks. And then you can check that. Well, you can check my math for all of the rest of them. So we take all 8 principal minors, we take their negative valuations, and we get some function on the vertices of the 3 cube. And this induces some regular subdivision on the 3 cube. And the claim is that every edge of this subdivision has direction either EI or EI minus EJ. Where the discrepancy is the EI comes from really we like dehomogenized something. And here, as I've attempted to draw, this breaks up the 3 cube into, I think, 4 maximal pieces. Have a tetrahedron, like a simplex on one side, a simplex on the other side, and then the middle octahedron is broken into 2 pieces along this square. And you can check this function is what's called submodular. So it's submodular. And satisfies sort of the analog of the 3-term Plücker relations, which in this 3 cube, the only condition is that if you look at, you have sort of 3 long diagonals along this octahedron, that the max of the sums of the function values along these 3 diagonals has to be attained at least twice. So the theorem that we were able to say at the end of the day is the following. So if we take the image of positive definite matrices under this map, and we look at the tropicalization, we get the following thing. Let's try and digest this a little bit. Let's start here. So we can, analogously to the Grassmannian, we can take something called the flag variety, where we look over all what's called complete flags. So this is a collection of linear spaces of all dimensions 1 through n, where each is contained in the next. And we could record the Plücker coordinates of each of these subspaces. So this lives in a product of Grassmannians, which we can think of as living in a product of projective spaces. If we take what's called the affine cone of this, so we just, for each projective space, we just add in the scaling that we modded out by. Then, so what do we have for every subset of 1 through n? We have, for every size, 1 through n, we have a subspace, L sub k of dimension k, and we have Plücker coordinates corresponding to that subspace. And so this naturally lives in a 2 to the n dimensional space. And if we take the tropicalization of this variety and we intersect it with what's called the submodular cone, then the image of this is exactly the tropicalization of the principal minor map. So in our 3x3 example, we had a 3x3 positive definite matrix, and we recorded all of the principal minors of it, the valuation of the principal minors. So that sort of lives up here. And what this is saying is that this is up to details equal to the tropical flag variety. And the element of the flag variety that we would associate to this is really the flag given by the upper justified rows of this matrix B. So here we would take a 1-dimensional linear space spanned by the all ones vector, a 2-dimensional linear space spanned by the first 2 rows of B, and the 3-dimensional linear space spanned by all 3 rows of B.
Is it obvious that any A of that form has a factorization where the B is upper triangular?
Yeah, great. So getting upper triangular, if you know that if A is really positive definite, all of the principal minors are positive and non-zero, then it's sort of not too hard to show that you can always factor into a matrix times its transpose where you get something upper triangular. There's a harder part of this theorem, which was very non-trivial to show, was that not only is this upper triangular, but it's upper triangular where if you fix any columns like we did before, like 1 and 3 when we did this example, so there we computed all of the 2 by 2 minors. The harder thing to check is that you can always factor in such a way where the top justified minor, which here was this one, is the one that contributes to the valuation. So when we did, that's the harder part of this as a theorem. So for example, when we computed this 2 by 2 minor A13, we said it's a maximum of various 2 by 2 minors of B. The one that actually mattered at the end of the day was the top justified one. We got a t squared, and it came as the square of this 2 by 2 determinant. And when we took different color, when we compared it to this 2 by 2 determinant, the valuation was higher, and so it didn't contribute. So that's the harder part of this as a theorem. Yeah. But yeah, just upper triangular is sort of one can get using linear algebra.
Sorry, I haven't taught linear algebra recently.
Yeah, I mean, it's not trivial linear algebra, but I promise it's like, I promise at the end of the day, it's linear algebra. Yeah. So to me, this is nice because this really relates two different notions of representability. One is really principal minors of positive definite matrices, and the other is being an element of the tropical flag variety. One of the next, so here's this theorem once again. One nice thing about this is that actually the tropical flag variety is something that has been studied before. So for example, by Brandt, and Zhang in 21, they studied the tropicalization of the flag variety over the complex numbers and compared it to something called the flag Dressian, which maybe I won't define, but which is essentially the set of M-concave functions on the 0, 1 cube. And that they showed that these were equal when n is equal to 5, but not for n equals 6 and up. So this one can think of as the analog of valuated matroids. And this is like representable, the analog of representable valuated matrix. And so one immediate corollary of this is that if we're interested in tropicalizing principal minors of positive definite matrices, then you get all M-concave functions on the 0, 1 cube for n at most 5, but not for n equal to 6, because it's sort of up to some small details really equal to the tropicalization of the flag dressing, or sorry, the equal to the tropicalization of the flag variety. Okay. How are we doing on time? Not great on time. Well, okay. Maybe in the, how many minutes do I have left? Not many. Can finish up quickly. Maybe I'll just as a parting thoughts, say okay, so this was really, we're interested in tropicalizing principal minors of positive definite matrices. And what we get, you should think of as like, it's a type A story. We get functions on the 0, 1 cube that induce regular subdivisions with edges that look like EI minus EJ. If you try to tell the same story, but you no longer require that your matrices are positive definite, you no longer have a type A story. You end up with a type B story. And this is so you get a story about delta matroids. So just as a very small example, here is a symmetric matrix. It's not positive definite. Its determinant is -1. If you look, you can record its principal minors. I should have done this over a valuated field, I now see. But essentially, if you start taking evaluations of things, so here, no, it's fine. So these two, the empty set and the whole determinant, are non-zero. The diagonal entries are 0. And so what you end up with is like, as a function on the cube, is that these coordinates get sent down to like -infinity, and you get an edge of this form, which is like E1 plus E2. So you get an edge direction that we were not allowed before when we started with positive definite matrices. And in general, it's the theorem of Boucher in 87, and if you have a symmetric or a skew symmetric matrix, and you look at the subsets that appear with non-zero principal minors, that you get something called a delta matroid. And using the theory of stable polynomials, so Peter Benden extended this to, rather than symmetric or skew symmetric, Hermitian or skew Hermitian. And so we were interested in trying to tell a evaluated version of this story. We could sort of analogously with matroids, if we have a function on the 0, 1 cube, could call it a valuated delta matroid if when you look at the regular subdivision induced by W on the 0, 1 cube, every edge is parallel either to EI or EI plus or minus EJ for some I and J. And then if you start with your favorite field with evaluation that has some sort of automorphic involution, for example, the field of complex Poisson series with complex conjugation, then if you take an n by n matrix over that field, that's Hermitian in the sense that its transpose is equal to its coordinate-wise image under this involution. Then you take the evaluation of its principal minors. This gives a function on the vertices of the 0, 1 cube. So what we're able to show is that this gives a valuated delta matroid. So the subdivision that this induces on the 0, 1 cube, all of the edges have this form. Okay. Maybe, well, I'll try and finish up, but just for a small example, if we were to work over the complex Poisson series and look at the following Hermitian matrix, where I is really I, right? I squared equals -1. This matrix is Hermitian. We can record the vector of 8 principal minors. Can see that we have valuation 0, valuation 1 for all of the singletons, valuation 0 for all of the sets of size 2, and valuation 1 for the set of size 3. If we look at the regular subdivision this induces on the 3 cube, all of the vertices whose coordinate sums are even stay at height 0. All of the coordinates whose vertices corresponding to odd subsets, we take minus valuation, are sort of pulled down to height -1. And so we get the following sort of big simplex as one of our chunks. And in particular, these edges are parallel to like EI plus EJ. Okay. Maybe in the interest of time, so I'll just mention one can also translate other notions of representability of delta matroids, in particular connecting to the orthogonal Grassmannian that was mentioned earlier. So any delta matroid that you can represent sort of using the orthogonal Grassmannian, one can also represent using principal minors of Hermitian matrices. Let's skip some stuff. And maybe just end by saying that so this gives another notion of representability of delta matroids. It becomes quickly apparent that most delta matroids are still not representable in this way. But this seems like a set that's worthy of study. So maybe I'll just end there and take questions. Thanks.
Thank you. Are there any questions?
Can I ask a question? Is there a notion of symmetric and skew symmetric that sort of makes sense in all types? You know, this was type A and B.
Yeah.
Like, is there a general Coxeter matroid story here?
I don't know. So I think Felipe's original story with the orthogonal Grassmannian was a type D thing. Was about this paper of Felipe from 2010 was really about even delta matroids. And the Fathy and skew symmetric matrices. So this was, you know, EI plus minus EJ. Yeah, I don't know if there's a general Coxeter story. I guess I'm really coming at from the standpoint of like minors of matrices, which I realize is not the usual way. But yeah, it would be great to understand better. David?
About minors of matrices, can you, so I guess the relations between minors of matrices are pretty mysterious in general. Can you say anything about like new relations or non-relations?
Yeah.
So
this is actually was my entrance to this as a project. But so Abeer, who's a joint co-author on this first paper. So we had looked at the image of the principal minor map without tropicalizing anything. And it's a beautiful story. Map. You can look at, you take the space of n by n matrices, or maybe you restrict to symmetric matrices, and over, your favorite field, and look at its image in R to the 2 to the n and say, what are the relations on this? Yeah, and in general, so for symmetric matrices, there's a lovely story. The polynomial relations. Polynomial relations come from so for n equals 3, there's a single polynomial relation, and it comes from something called Cayley's 2 by 2 by 2 hyperdeterminant. You can go look up. And then for and then actually you can get polynomial relations for higher n using a large group action. In particular, this was a story. So Luc Ouding basically showed that set theoretically you can take the orbit of these under a large group action and you'll get a set of defining equations. So defining equations are known and nice. They're not the easiest to work with. And then for general n by n matrices, you don't need to restrict to the real numbers, but you could. It's actually, so people know some defining equations, but it's actually a full set is unknown. So it gets a little bit worse.
Even for the principal minors.
Even for the principal minors. But yeah, so this is something that I had studied with Abeer in her thesis, and sort of we put out 2 papers really studying the relations on the image of this map. And maybe I'll just say the most useful tool that we got as part of this was really something called Dodgson condensation. Which is a nice relation on involving the principal minors of a matrix. And so that was sort of the engine behind a lot of this analysis.
Very cool.
Yeah, but it's a lovely story independent of tropicalization.
Awesome. Thanks.
Any other questions? Yes, there's a comment in the chat from Christian Gray that they have some work on Coxeter matroid representability for this.
Oh, great. How do I get to the chat? We have some, oh yeah, great. Rank 2. Yeah, okay, great. I will I'll write that down and check it out. Yeah, thanks. Yeah, absolutely. One of the reasons I wanted to talk about this in the seminar is that there's a lot of literature out there, and I'm pretty sure we have not managed to find all of it. So it seemed like a good opportunity to find out what's out there.
Any more questions? Let's go ahead and thanks.